Hey guys, so hopefully by this point you have already taken the pre-mock and now you're getting ready to review it. I think the pre-mock is going to be most representative of his real exam because these are all of his recent multiple choice. So I think it would be really useful if you guys wrote the answers, had your work on hand when you get ready to take the real exam. Okay? So we're going to start with multiple choice 1, and it says, which of the following molecules is chiral? So when anybody says molecules, it's the same thing as compounds, just so that clears up any confusion. Alrighty, so now my approach when I'm starting these questions is the first thing you want to do is look for molecules that have chiral centers, right? So when you're doing this, first thing you want to do, which molecules have chiral centers? That looks like a Z, but you know. Okay, and now once you find the ones that have chiral centers, you want to make sure that the overall compound isn't meso, because meso compounds are achiral compounds with chiral centers in them. Okay, so the next question is going to be, for the molecules or compounds that have chiral centers, are they meso? Okay, so these are the two things you want to ask yourself when you're doing this kind of a question. I'm going to put the definition of meso again. So, meso compounds have chiral centers, but are achiral. Oopsie. Achiral compounds or molecules. So in your head, you should be thinking right now, what are the requirements for a meso compound? And I'm going to go over them with you in a second. I'll give you a second to think about it. Okay, so meso compounds, as you guys should have come up with, have at least 2 chiral centers, have a line of symmetry, and have equal numbers of R and S chiral centers. So for example, if there are 4 chiral centers in your molecule, 2 of them will be R and 2 of them will be S. Okay? So these are the requirements for meso. Okay. Now with that in mind, we can go ahead and start looking at 1, 2, 3, 4, and 5 and figure out if the molecule is chiral or not. Okay, so starting with number 1, the first thing I want to do is see if I can assign priority on the BR first. And then if I can, I want to see if the molecule is meso and assign priority for all of them. Okay, when I say the BR, I mean the BR carbon, right? Because this is what has chirality, not the BR itself. So the highest priority is obviously going to be your halide and your halogens. Those are always going to come first. So your BR is going to be on a number 1. Then you want to compare the different sides of the ring, right? So you want to move from this carbon and look for the first point of difference on either side. So moving this way, you have a carbon bonded to 2 H's. Moving this way, you have a carbon bonded to another carbon and 1 H. So this side, since it weighs more, or like has the point of difference earlier on, this is going to be the higher priority than the other side. Okay? So with that in mind, we're going to rank this side of the ring as 2 and this side as 3. Because your H coming off of your chiral center is already on the lowest priority, you don't have to switch the stereochem. So whatever you get is what it is. So going in order, you can go 1, 2, 3. And in this case, this is a S chiral center. Okay, I'm going to erase my work and then move on to the other ones. Alrighty. Now I'm going to change color just to keep everything organized. We're going to go to this carbon over here with the methyl coming off of it. In this case, because you have a methyl coming off of it, you have to compare the rings first because those are going to be heavier. Those are going to have more points of difference than just the CH3 by itself. So moving to compare the rings, if you go to this side, you have a carbon bonded to 2 H's. Okay? And if you go to the other side, you have a carbon that's bonded to a Br. So this side is going to take priority. Okay? So this is going to be number 1, and the other side of the ring is going to be number 2. Your last priority, as far as carbons goes, is going to be your methyl. Since your H is on a wedge, you're going to have to switch the stereochem for whatever you get. So in this case, we get 1, 2, 3, and this is an R. But because, oops, I don't know why I did that. Oh, that's great. This is an R, but because we have to switch the stereochem, we're actually going to be making it S. Okay, so I'm going to erase. This is R, this is S. I mean, oopsie, they're both S. All right, moving to the other side. Let's work on this carbon here. Same thing as before, your Br is going to be priority number 1. Then you're going to compare the rings. This one has a point of difference earlier where the methyl is coming off of it, making it higher priority over this carbon here with 2 hydrogens coming off. So the top half of the ring is going to be number 2, and the bottom half of the ring is going to be number 3. Because, again, your H is on the wedge, you're going to have to flip whatever stereochem you get. So although we get an S counterclockwise ring, we have to flip it. So this one's actually going to be R. Okay. Now, for the last chiral center, we're, again, comparing different carbons. So your methyl is not going to be 1 or 2. You're going to have to compare the rings first. So we're going to go for the first point of difference like we did for the past 3. This one has 2 H's. This one has a Br on it. This one down here is going to be higher priority. Then the second half of the ring is still heavier than the methyl on its own. So that's going to be 3. And then the methyl is going to be, well, actually I forgot to even include 1. So that's on me. This is 1, 2, and then the carbon or the methyl is 3. Okay? So now we can draw the circle in. And because the H is on a dash, we don't have to flip the stereochem. And this is R. So let me erase. Now, in the end, we have S, S, R, R. So we can see that we have equal amounts of S chiral centers and R chiral centers. But do we also have a plane of symmetry? Yes, we do. So if you cut your molecule in half like this, and you fold it over, I wanted to show you guys, but I realized you can't see. So if you fold it over, you see that you do have a plane of symmetry here. So number 1, although it has chiral centers, it is meso. So it is not chiral or achiral. Okay. Alrighty. Let's move on to number 2. This one is relatively easier because looking at it, you realize that you actually can't designate the stereochem for either this center or this center. Reason being is because the chains that they are bonded to are identical to each other, and I'm going to explain what I mean. So let's start with this carbon that the Br is bonded to, because obviously it's easier to work with Br. So it's very obvious that your halogen is going to be number 1, but now you want to compare the rings. When you try to look for a first point of difference, you see this one goes up, over, up, over. These are identical so far. It's identical all the way to when you have a substituent. What that means is you can't rank priority between these two sides. They're equal to each other because this carbon is bonded to the same thing on both sides. Does that make sense? Hopefully you get. I know you guys can't answer, but hopefully it does. And if you do that for this chiral center, you're going to see the same thing. You can't rank the different sides of the ring because this is exactly the same as this. Okay? So this one has no chiral centers at all. So you would call it no chiral center, not chiral. Not a chiral compound or molecule. All right, number 3, same thing. Because they're equidistant from each other, so what I mean when I say that is if you're looking at the rings on either side, let's do the Br one, right? Because Br is going to be number 1. This is 1, 2, 3, 4 is where you get your first point of difference on the left side. And when you do that on the right side, 1, 2, 3, 4, same thing. Your first point of difference is the exact same amount of carbons away on both sides. So in that sense, they're equal to each other. This side of the ring is equal to this side of the ring, and you can't assign chirality. Anytime you see them, like if you only have 2 chiral centers and they're opposite of each other on the ring, that's a sign that it's not going to be a chiral compound. So same thing as before, no chiral centers. Just because they designate the wedge in the dash, that doesn't make it a chiral center, by the way. Because for something to be chiral, it has to be bonded to 4 unique things. In this case, these 2 rings are equal, so it's not bonded to 4 unique things. So no chiral center, not a chiral molecule. Okay. So moving on to number 4. Again, this is the exact same compound as number 2. It's just Br is now equatorial instead of axial, but that doesn't make a difference when you're thinking about chirality, right? So in this case, again, if you look at this carbon, you give Br number 1. When you compare the different sides of the ring, again, you see that they're the exact same. It's 1 carbon, and another carbon bonded to a carbon. Here it's 1 carbon, another carbon, and the carbon bonded to the carbon. Since they're opposite each other, this is not going to have any chiral centers. And the molecule is not chiral. Okay. Number 5. Alrighty, so we see that they're not opposite to each other. So that means the different sides of the ring are going to have priority. So you know that this is going to be, or this compound is going to have chiral centers. Now the question is it meso or not? So starting with this carbon up here, you're going to rank priority. Obviously the halogen is going to get number 1. And now you're going to compare the 2 sides of the ring. So going this way, this is just a CH2. Same thing here, another CH2. So you have to keep moving. This one is a carbon bonded to a Cl. This one is another CH2. So this side is going to have priority over the other side. Okay? So this side, so this side of the ring is going to be 2, and this one is going to be 3. So you're going to go 1, 2, 3. And then in this case, it's S. And since your hydrogen is on a dash, it stays as S. Okay. Now let's look at number 5. So obviously, again, halogen number 1. We already ranked the sides of the molecule before. This one has the point of difference sooner than this one does. So the side to the left is going to be number 2. And then the side to the right is going to be 3. In this case, you're going to get R. And because your H is on a dash, you're going to leave it as R. So now we have R and S designations. Like that's pretty much a sign that you have a meso compound. But the last thing you want to do is make sure that there's a plane of symmetry. And in this case, there is. Straight down the molecule. So this is meso and achiral. Make sure you know that achiral is not the same thing as not chiral. Achiral molecules are meso. Not chiral molecules have no chiral centers. It doesn't matter for this question in particular, but he might ask you another question later. So, which of the following is chiral? None of them. So the answer to this one is going to be E. None are chiral. Technically, he should have said R. Don't know why he said is. Okay, so multiple choice 2 asks, which of the following statements are true about the combustion of propane? So, before we get started with the overall reaction, there are 2 things to remember about combustion in general. So, combustion reactions are always spontaneous. always spontaneous. And combustion reactions are always exothermic because heat is always going to be released. Okay. So that means we can eliminate number 2 because it says the reaction is spontaneous only when a flame is present. You don't need a flame present to do combustion. So 2 eliminated. And you know 1 has to be in the answer. So you could eliminate D and E. Okay? So moving along. I personally, the way I did this in order is the next thing I did is I drew out the reaction, the combustion of propane. You don't have to do this, but I chose to. And it got me the answer. So I'll keep moving. So the way you could figure out the molecular formula of propane first, because you're going to need to know how many H's there are, is to remember the rule that CnH2n plus 2. So if they give you the number of carbons, you can multiply that by 2 and add 2 to find the number of hydrogens. In this case, it's propane. So prop means 3. So it's going to be C3H8 because 2 times 3 is 6 and then plus 2 is 8. So everything is a gas when you're doing combustion, and then you have to figure out how much water and how much carbon dioxide it's going to make. If you have 3 carbons on your left, you're going to need 3 moles of CO2 on your right. And then if you have 8 H's on your left, you're going to have to make 8 H's on your right, or 4 moles of H2O because H2. And then that leaves you with, once you balance out the equation, 5 O2 to even out the number of oxygens. Okay, so now you want to compare whether or not enthalpy is positive or negative. So enthalpy is the heat of the system, and if heat is released, it's exothermic, and if heat is absorbed, it's endothermic. So I'm going to write that down. Enthalpy, or delta H, is the heat of the system. So exothermic reactions, heat is released, and delta H is going to be negative delta H. Endothermic reactions, Okay, I can't write today. Heat is absorbed, and you're going to have a positive delta H. Okay? So for entropy is represented by delta S, and this is just the disorder of the system, right? So basically, if you start with less molecules and go to more molecules, that's an example of increase in entropy. So if heat is, not talking about heat anymore. If your disorder increases, so disorder increases, you're going to have a positive delta S. And if your disorder decreases, you're going to have a negative delta S. Okay, so now we can look at our propane reaction. Like I said in the beginning, anytime you have combustion, it's going to be exothermic. So that immediately means that enthalpy is going to be negative because exothermic. So you can eliminate number 4 and any answer choice with 4 in it. So that's C. And 3 and 5 both say that the enthalpy is negative, but now you have to think about the entropy. So in this case, you do have to pay attention to the actual formula, which I will outline here. And on the left side, you start with 6 moles of gas because you have 5 moles of O2 and 1 mole of propane. So 6 moles of gas. Sorry, O2 is a gas. I didn't fill it in. And then on the right side, you end up with 7 moles of gas because you have 3 moles of CO2 and 4 moles of H2O, and everything in this reaction is a gas. So you're going from less molecules to more molecules, which means that you're going to have an increase in entropy. So entropy is going to be positive. So the correct answer is going to be 1 and 3, and that is A. Okay? A little bit of Gen Chem review. Okay, so multiple choice 3 asks, in which of the following compounds do the sigma bonds have the greatest amount of S character? So the way you want to think about bonds and S character is as follows. So for single bonds, they are going to be sp3 hybridized, and that means that they're going to have 25% S and 75% P character. Because if you're thinking about S, P1, P2, P3, there's 4 parts to the whole. 1 of them is an S, and 3 of them are P. Okay? So for double bonds, they are going to be sp2 hybridized, and that means 1/3 is going to be S character, and 2/3 are going to be P character. Finally, for triple bonds, they are going to have your highest S character because they're going to be sp hybridized, which means that S is going to be 50%, and P is also going to be 50%. Okay? So looking at multiple choice 3, you can go ahead and pick B right off the bat because it's the only triple bond there. But really quickly, we can go over the rules of hybridization in general just because he might ask you another question. So the only things that count as hybridized are sigma bonds and lone pairs, right? So when you're thinking about a double bond that has 1 sigma bond in it and the additional bond is a pi bond. When you're thinking about a triple bond, it has 1 sigma bond and 2 additional pi bonds on top of it. So keep that in mind when you're thinking about hybridization in general. So we'll go through and do Cl2. So Cl is going to have 3 lone pairs and 1 sigma bond. So assigning priority, I like to number it by using S, P, P1, P2, all that. So I'll do S, P1, P2, P3. So this one is going to be sp3 hybridized. Looking at B, we have 1 sigma bond, well, 2 sigma bonds, really, because you have 1 bonded to the H. But 1 sigma bond in your triple bond, and then 1 sigma bond bonded to the H. So this would be an sp carbon. Looking at water, you're having 2 lone pairs on the O and 2 sigma bonds. So that's going to be sp3 hybridized, because 1 S, P1, P2, P3. Just a review on how to tell the hybridization of orbitals. Oops. So looking at this carbon, you have 1 sigma bond here and 1 pi bond, so that doesn't count. And then 2 sigma bonds to each H. So it's going to be S, P1, P2. So sp2. And then finally, you have a straight alkane, and that is going to have 4 sigma bonds. So it's going to be S, P1, P2, P3. So hopefully we did not forget that. And the answer to multiple choice 3 is going to be B because it's the only triple bond we have. Okay, so multiple choice 4 says to rank the following compounds in order of increasing pKa. So just a quick reminder about pKa's. If something has a high pKa, that means it is not acidic or not very acidic. And what that also means is that it's going to be relatively basic. If something has a low pKa, it's going to be very acidic, not very basic. Okay, so keeping that in mind, if they're asking us to do in order of increasing pKa, your more acidic things are going to come down here, or early on in your answer choice, and your less acidic things are going to be at the end of your answer choice. Okie dokie. So now when we actually look at the molecules that we have an alcohol, 2 carboxylic acids, a CH4, and a amine. I will give you the pKa's for those in case you want to write them down. But right off the bat, you should know that carbons are going to be your least acidic, because when do you ever see a carbocation? Only in situations where a lot of reactions are occurring. The reason why these reactions occur with carbocations is because carbocations are very unstable and they're unlikely to happen. Then you could see an NH3, an amine, and you know amines are relatively basic just because we've been doing this for so long. They also have the lone pair that can accept another H. Then you have your alcohol, which is always going to be a little less acidic than your carboxylic acids. The real trouble for this question comes between comparing the 2 carboxylic acids, but we'll get to that in a minute. So pKa of CH4, is going to be around 50. The pKa of an amine is going to be around 35. The pKa of an alcohol is normally around 16 to 18. And finally, the pKa of a carboxylic acid is usually around 4 to 5. Okay, so with that in mind, you know that 3 is going to come at the end because carbons are least reactive, least likely to give your H's up, and that means they're going to be less acidic. Less acidic, high pKa. So they're at the end. Okay, so you can eliminate A, E, and C. Now we're going to be comparing the 2 carboxylic acids is what it comes down to. And the only way to distinguish them is that you notice that one has a Cl on it. Well, chlorines are very electronegative, so they take part in the inductive effect. So inductive effect increases acidity because now that you have an electronegative group next to your carboxylic acid, that makes it more likely to resonate the lone pairs that form when you lose the H. So that means the Cl likes having negative charge near it, right? So whenever you have a carboxylic acid, after it loses the H, you get a negative charge there. If you have a Cl nearby, when it resonates to the other O, I will show you in 1 second. It is now closer to the Cl, and because the Cl is electronegative, it's totally cool with that. It helps the molecule balance out the extra negative charge. So whenever you have a halide or a halogen nearby, that means it's going to decrease the pKa of that group. So that means 2 is going to be your most acidic, and then 5 is going to follow up. And that leaves B as your answer to multiple choice 4. Okay, multiple choice 5. What is the correct stereochemical designation for the following isomers of 3-chloro-2-butanol? So the first thing I wanted to do in this situation is number my carbons, so I knew which was 2 and which was 3. So they actually tell you that the OH is going to have priority, but in general you should be aware that you should number it where the OH is going to have the lower number than the chlorine, because an alcohol is a functional group and a halogen or a halide is a substituent. So this carbon would be 1, this is 2, 3, well, oopsie, 4. So this side is going to be 2, this is 3, this is 2, this is 3. Okay, so I like to keep that in my head. It might confuse you with like assigning priority. So if that bothers you, like go ahead and erase it, but I personally like to keep it there. So looking at carbon 2 of compound 1, we're going to try and assign priority. So obviously the first thing you want to do is give OH the priority, because alcohols are going to have more priority than carbons and the rest of the chain, and definitely the hydrogen. So OH is going to be number 1. Then you want to do the rest of the chain, and finally the methyl. So that is going to give you S, but because your highest priority is on the dash and your lowest priority is on the wedge, so your H is on the wedge, you're going to flip it. So it's R, I mean it's S, but it's really R. Okay, so hopefully that makes sense. I'm going to erase just to keep things neat. So you know for molecule 1, it's going to be 2R. So you could eliminate any of the answer choices that are not 2R. So that's D and B. And looking at carbon 3 of compound 1, you want to do the same thing. So in this case, your halide is going to be number 1. And then the rest of your chain is going to be 2, and the methyl is 3, because the methyl weighs less than the rest of the chain, and halogens are always first priority. So in this case, you're going to go 1, 2, 3, and that gives you S, but because your lowest priority, the H, is on the wedge, you're going to flip it. So it's S, but it's actually, oopsie. So it's S, but it's actually R. Okay. So 3 is going to be R. And now you want to go in your answer choices and just eliminate anything that doesn't give you 3R. And you actually already get your answer right there as C, but we can keep going just in case. So at molecule 2, looking at carbon 2, your OH is going to be number 1 because, again, alcohols get priority, then the rest of the chain, then the methyl by itself, and that gives you S. Oh, wait, does it? No, oh my god, I'm such a liar. It gives you R. As soon as I did that, I was like, wait, no, because it's clockwise. So 2R, and then moving on to carbon 3 of molecule 2, halogen's going to be number 1, the rest of the chain, and your methyl is last. Oh, the reason you don't have to switch it in these cases is because your lowest priority, the H, is on the dash for both carbon 2 and 3 of compound 2. So following the path that we drew out, this is going to be S. S. So now it's a good opportunity to check our answer and see if for this one it is 2R and 3S, and it is. So that's a good sign that we already got it right. So the answer to multiple choice 5 is going to be C. Okay. Multiple choice 6 asks, which of the following reactions results in the formation of a pair of diastereomers? So that means there has to be one chiral center that is unbothered or untouched by the reaction, and then a new chiral center has to be formed. Okay? So let's go over what each of the reactions does, because I think that's the most important things with these questions. So HBr by itself is going to give you, oopsie, that's kind of ugly, is going to give you the Markovnikov addition of a Br with rearrangement. With rearrangement possible because of the carbocation intermediate. So when I say the Markovnikov addition, I mean the more substituted side of the double bond will take the Br if it's Markovnikov. If it's anti-Markovnikov, that means the less substituted side of the double bond will take the Br. So, moving on to HBr over Ror with UV, oopsie. This is what we just learned about in the radicals section. This is going to give you the anti-Markovnikov addition of a Br without rearrangement. So, anti-Mark addition of a Br without rearrangement. I spelled that wrong. Rearrangement. Okay. Then D is the hydroboration reaction. So I'm going to write hydroboration, but on your own notes, you should write out exactly what it is, the first and second step. So this is going to give you the anti-Markovnikov addition of an OH without rearrangements. Okay. So that means the OH is going to add to the less substituted side of the double bond. Finally, you have H2PT. H2PT is going to be the syn addition, of two hydrogens across a double bond. Alrighty. So I'm going to erase this, and then we'll start doing the actual answers to the question. Okay, so looking at A, without doing the entire mechanism, because by this point you guys should definitely know it, and if you don't, you could either look at my old reaction video, or my old premock videos, or his notes, but we know that the H is going to add to the less substituted side, leaving a carbocation on the more substituted side of the double bond. So starting with this, let me make sure. Your intermediate is then going to be this. And then you're going to have a hydride shift. That H is kind of ugly. Then you're going to have the hydride shift from this H on the dash over down here to give you the more substituted carbocation, which is now going to be tertiary. Oops, actually that's okay. And then your Br is going to add to the carbocation, and your end result is going to be CH3 and Br plus an enantiomer. See, the issue is here that we actually messed with the one chiral center that was already on it, and now we only have one chiral center in our product. So that means you're not going to end up with a pair of enantiomers from A. So you can eliminate A. Actually, I'll just put the product in next to it, just to keep things organized. Okay, so A is not the answer. And now we can move on to B. Okay. So it's going to be the same reaction as before. You're going to have your H add to the less substituted side of the double bond and the carbocation on the more substituted side of the double bond. So it's going to look like this. Now the issue is that you can't actually have a hydride shift in this situation because the tertiary carbon, this one, is too far away. It's more than one carbon away. So in this situation, you can't have a shift. You would only be able to have a shift from the adjacent carbons, and in that case, it wouldn't happen because they're equal to this carbon. So now the Br is going to add directly to the carbocation that we just made, and you're going to get this plus diastereomer. Because you're not affecting the original chiral center that was there, you're just adding a new one. And the Br is going to add both on the wedge and on the dash for this type of reaction. So B is actually going to be your answer, but we can keep going. Okay. So now HBr over Rohr. All that's going to do, I'm not going to go through all the steps because we're going to go through that in SI tomorrow. Well, when you guys see this, we will have already gone through it. But basically, it's just going to add the Br to the less substituted side of the double bond. There's not going to be any rearrangements, so it's quite simple. It's just going to be that. Reason that this is not a diastereomer is because your Br is terminal. So now that means you're bonded to two H's, and that means it's not a chiral center. Okay, so C is not your answer because you're not going to even get an enantiomer, you're just going to get a Br added to it. Okay. Moving along to D, this is just going to be the anti-Markovnikov addition without rearrangements. So it's going to look exactly like your product for C, but instead of a Br, it's going to be an OH because it's hydroboration. So drawing it out, you just add the OH to the less substituted side of the double bond, and this is your product. Again, the OH carbon is not a chiral center because it's bonded to 2 H's, and you need to be bonded to 4 things to be unique, so you're not going to get the pair of diastereomers that you want. Okay, so not D. And finally, E is just the syn addition of 2 H's. So you're going to go from the double bond to the single bond. Just like that. I don't think you guys have to know the mech for this one, but I would know the mech for A, B, and C. Well, A and B are the same, but for B and C. C, I guarantee you he's going to ask you questions about the mech for propagation and HBr over roar and termination, all that good stuff. Oops. Okay. So, like I said, the answer to this one is going to be B. Okay, so multiple choice 7 says, what is the product of the following reaction sequence? So the first thing you have to do is go one by one and figure out the answers. So A is the free radical bromination of an alkane, and that's going to add a Br. Let me write it in. Adds a Br to the most substituted but available carbon. So obviously this carbon over here, it can't add to because there's already 4 bonds on it. So the next most substituted is this one over here. Okay? So looking at actually, I'm going to erase and I'll draw the answer in. So if you're adding the Br to the most substituted available carbon, it's going to be this carbon here because this one is least substituted, this is most substituted, but it's not available because it already has 4 bonds. It's not, NBS doesn't interfere with bonds that are already on the ring. I mean, on the compound in this case. Okay, so it's going to look like that. Let me make that actually a little smaller. Okay, so the next reaction you guys should all recognize is an elimination reaction using a big bulky base. So what that's going to do is pull off the terminal hydrogen, make a double bond where it was, and kick out the Br. So I'll show you down here really quickly. So terp butoxide is going to come here, and it's going to pull off this H. That's going to create a new double bond, and the double bond is going to kick out the Br. So the product of this reaction is going to look like this. Okay. Alrighty, and then the last step is hydroboration. I know he left off the THF, but it's still considered hydroboration. And as we remember from the earlier question, this is going to be the anti-Markovnikov addition of an alcohol with no rearrangements, and it's adding it to an alkene. So if we're adding it to this alkene with no rearrangements, the OH is going to add to the end of the compound. Like this. And that gives you answer E for multiple choice 7. So multiple choice 8 asks us to rank the bond lengths in increasing order. So the shortest is going to go first and the longest last. In general, triple bonds are going to be shorter than double bonds. Double bonds are going to be stronger and shorter than single bonds. And finally, CH bonds are going to be shorter and stronger than any carbon bond. So that includes double bonds and triple bonds. So CH is going to be stronger than C triple bonded to another C, C double bonded to another C, or C single bonded to another C. CH is going to be stronger and shorter than all of those. All right, so with that in mind, we can go ahead and tackle this question. Right off the bat, you can see that number 2 is pointing to a CH bond. So that's going to be your shortest bond. Like I said, it is going to be shorter than any carbon-carbon bond. So you can eliminate anything where 2 is not the first answer. And that actually gives you your answer right away, which is B, because it's the only one with 2 as number 1. So then you're comparing a triple bond, a double bond, and a single bond. So 4 is going to be your triple bond. That should be your next shortest. And in B, we can see that 4 does come next. 1 is going to be your double bond. And we can see that that comes next because it's going to be less or more short than the single bond, but less short than the triple bond. So it's going to be 4, 1, and then finally 3 is our single bond. And that should be our longest bond. And in B, we see that that is our longest bond. So multiple choice A was relatively easy. He's just quizzing you on whether or not that you know that CH bonds are the shortest and the strongest bonds. So multiple choice 9 asks, what is the pKa of an acid if at pH 5 the ratio of undissociated acid to conjugate base, HA, acid, over A minus, which is the base, is 1 times 10 to the negative 2. So to do this problem, you have to remember Henderson-Hasselbalch equation, which I will write in for you guys. Henderson-Hasselbalch is pH equals pKa plus log of base over acid. So in this question, he tries to trick you guys a little bit because he gives you the acid over the base. And he says that that's 1 times 10 to the negative 2, or 0.01. So instead, you have to give the inverse of that, or do 1 over 0.01. So 1 over 0.01 is the same thing as 100. And this will give you the base over acid ratio that you need to do the Henderson-Hasselbalch equation. So now you could do 5 equals pKa, 5 being the pH that they gave you in the question, plus log of 100. Log of 100 is 2. So 5 equals pKa plus 2. 5 minus 2 equals 3, so pKa is 3, and that gives you the answer B to multiple choice 9. Not a hard question, especially since you guys will have calculators, but you do need to remember this equation. Featuring my dog in the back. Okay, so multiple choice 10 asks, in which of the following reactions is the correct major product shown? So like I said, the first thing you want to do is figure out what each of the reactions do. So in general, H2SO4 over H2O is going to be the Markovnikov addition of an OH across a double bond with rearrangement, because there's a carbocation intermediate. Okay? So now we have oxymercuration, which is the HGOAC, H2O, H2O, comma, THF, and then NABH4. So I'm just going to write oxymerc, but you guys should write out the reagents and the solvents and the different steps. So this is going to be the Markovnikov addition of an OH without rearrangement. Because there is no carbocation intermediate. There's actually a bridge. Oh my god. Oops. Okay. So then you have hydroboration, which you guys should already know from the other questions, is going to be the anti-Markovnikov addition of an OH with, oh my, what did I do? Without rearrangement. Sorry, there was a line. And then H2SO4 again, and then another hydroboration. When I'm referring to the hydroboration, I mean these ones. Again, he didn't put THF, but you know that it's that reaction. Alrighty, so now we can look through the answer choices. Alright, let me erase. Actually, I'll write out the oxymerc one, hydroboration one, just in case people are skipping around. So, hydroboration, anti-Markovnikov addition of OH across a double bond without rearrangement. I can't fit it, but you know. Okay, now we'll start the actual question. So for number 1, you're going to have the rearrangement with H2SO4. So I will draw out like the intermediates, but right off the bat, you know that the OH should end up here. So you're going to have this carbocation intermediate, the H is going to add here, and then you're going to have a hydride shift. So you're going to have the H here, that's going to scoot over. I'm not going to draw the mechs for all of these because it's tedious, and I already did most of these mechs for the last exam. So if you want, you could go back to the old videos or look at his notes, but I'm pretty sure by now, most of you guys know this. And the new carbocation will end up here. And then finally, your OH is going to add here. So that's what the product should look like. However, they did a methyl shift or something without even adding the OH in the right spot. So A is incorrect. Moving on to B, this is the oxymercuration reaction. So like I said, you're going to have the addition to OH Markovnikov without rearrangement. However, in this case, they did do a rearrangement as if the carbocation moved up here, which would not happen. You guys don't have to know the mech, so it doesn't even matter. But what generally would happen is this double bond is going to turn into a bridge with like the HGOAC, and then the OH would attack the H2O and then get deprotonated, but I'm just going to say OH for ease of mech. It would attack the more substituted side, and that would be that. So B is not the answer because it shows a rearrangement. Letter C is hydroboration, so you want the anti-Markovnikov addition without a rearrangement. And that's exactly what it shows. So if it were Markovnikov, the OH would add here because that's the more substituted side. Since you want the anti-Markovnikov, the OH should add here without the double bond in the product, and that's exactly what they show. So the answer to this question is C. Let's go and check D though, just in case. That might be the right answer. Okay, so what would happen in this situation is you're going to have this as an intermediate. Oops, my bad. And then you're going to have a hydride shift here, because remember I said that H2SO4 is the one with a carbocation intermediate. And then you're going to have this as your new carbocation, and then the OH is going to add there, giving you this as a product. However, that's not what we see in our picture. We have the OH as if we did a oxymerc reaction, which we didn't. So D is incorrect. And last but not least is E. And the reason that this is incorrect is because you see a methyl shift has occurred. and that would not occur during a hydroboration reaction because there are no shifts during that. So you can go ahead and just cross that out. So the answer to multiple choice 10 is going to be C. Okay. Multiple choice 11 asks, which of the following cause the greatest decrease in a compound's solubility in water? So the first thing you have to remember when you're doing this type of a question is that like dissolves like. And this will make more sense in a minute. So if water is polar, which it is, that means it will dissolve polar substances very well. If you're trying to decrease a substance's solubility in water, then you want to make it less polar, okay? So now we can go through the answer choices. When you're increasing the polarizability of the electron cloud, you're literally making it more polar. So it's not A, because you're trying to make it less polar, so it won't dissolve in the polar water. Increasing the dipole moment is, again, the exact same thing as making something more polar, because now there's more pull on the electrons, so that's the same thing as making it polar. So it's not B. Increasing the size of the molecule's alkyl chain. So what this is saying is that, say your molecule looked like this. If you increase the size of its alkyl chain, that means you're making it like this. You're adding a bunch more carbons. And carbons, because they're bonded to either another carbon or hydrogens, are generally non-polar. So if you're increasing the size of a molecule's alkyl chain, you're adding more non-polar atoms to a molecule. Therefore, you're making the overall molecule less polar. So the answer to multiple choice 11 is going to be C. And then going through the rest, just because increasing the strength of the hydrogen bonds, that's actually a good thing. That will definitely make it more easy to dissolve in water because water likes H bonding. Increasing branching in the molecule's hydrocarbon chain. Okay, so this is not the same thing as saying you're adding more carbons. This is saying, okay, say you have this molecule here, then you're increasing the branching, so you would be doing this. And this is actually better to dissolve in water because then you have more hydrogens coming out versus carbons. Because when you change this carbon to over here, you're adding another hydrogen. So that means it's one more hydrogen that can H bond. So all of these would increase its polarability and then increase its solubility in water, except for C. So C is the answer to 11. Multiple choice 12, which should probably look pretty familiar for most of you guys, is what is the correct IUPAC name of the compound shown? Okay, so the first thing you want to do is try and name the compound on your own, or at least number it. When you're comparing the functional groups, know that the only functional groups on here are the alcohol and the alkene. The halide is, or like the chlorine, is not a functional group, so it's not going to get numerical priority right off the bat. So the alcohol is going to get numerical priority, so it's going to go 1, 2, 3, 4. Now you want to make sure that you include the double bond in the chain. So even though numbering this way would give you a longer chain, you have to include the double bond. So that's 5. So it's going to be pent. So you could get rid of A and you can get rid of C right off the bat. Now what you want to do is figure out if, oh, well, I guess they're both E. Let's actually double check and make sure it is E before we continue. So on the upper side, let me erase. So on the chlorine side, you have an H up here and a Cl here. That makes the Cl obviously more important. So when you're comparing the other side, you're comparing an ethyl versus the rest of the chain. So the rest of the chain is going to be more important than the ethyl. Since these two are diagonally across the double bond, it's going to be an E double bond. Okay? So now all you have to do is just make sure you named it right. So the difference is this one says 4-ethyl and this one says 2-ethyl. Considering we numbered it 1, 2, 3, 4, you know that the ethyl is supposed to be on 4 and that D is going to be the right answer for multiple choice 12. Okay, so multiple choice 14 asks, which of the following compounds has the least exothermic, the least negative, catalytic hydrogenation? So basically, the more stable the alkene is, the lower or the less negative the heat of hydrogenation is going to be. So more stable alkene equals lower delta, well, least negative, I should say. Least negative or least exothermic, whatever works for you guys, delta H. Okay? So when you're thinking about the stability of alkenes, as usual, you want to think of how highly substituted it is. So increased stability of alkene equals highly substituted alkene. Alrighty. So now we can go ahead and compare the different alkenes. So number 1 has an alkene, or I shouldn't say number 1. A has an alkene that is fully substituted here and then half substituted here. So that's okay. B has an alkene that is half substituted and then one that is 3/4 substituted. So it has 3 carbons on it, but 1 H. So that's not going to be our least negative because already A is going to be less negative than B because this alkene is more highly substituted than this alkene. Okay, so it's not going to be B. So C has one that's half, and then it has one that's terminal. So this one's only substituted in 2 places. So that's not very good. Already A is still going to be more stable than C, so it's going to have a lower heat of catalytic hydrogenation, or less negative, I should say, not lower. So it's not going to be C. Then D is pretty similar to A. They have one that's substituted on all sides and then one that's half substituted. So it's 2 carbons and 2 H's. The difference between D and A is that D is conjugated. So these double bonds can actually resonate with each other, whereas the ones in A cannot resonate because they're too far apart. So D is actually going to take over A in this one, and we can cross out A. Now we can compare E. While E does have double bonds that are conjugated, meaning that they can resonate with each other because they're right next to each other, they're both half substituted, whereas D has one that's fully substituted. So our answer to 14 is actually going to be D, and not E. Okay, so multiple choice 15 says, which of the following is not a nucleophile? So when you're thinking of what isn't a nucleophile, it's important to understand what is a nucleophile. So a nucleophile is nucleus loving. So in general, a nucleus is going to be a region of low electron density. For example, a carbonyl carbon is a nucleophile because when it resonates, it has a partial positive on it, on the carbonyl carbon. Okay, so in general, the types of things that want to attack this are going to have negative charges or lone pairs. In general, they're going to be basic. Okay, so keeping that in mind, we can look in our answer choices for which one doesn't have a lone pair or isn't anionic. Okay, starting with A, we have a OH anion, and this is has both negatively charged and has a lot of lone pairs. So this is definitely going to want to come and attack a nucleus. Good job, Stephanie. It's like, it gets confusing when it's so many words, but whatever. So long story short, A is actually going to be a nucleophile. B is actually a Lewis acid, BF3. And instead of having a lone pair up here, it actually has an open orbital to accept electrons. So this is not a nucleophile. Instead, it would be an electrophile because it wants to accept electrons. So your answer is probably going to be B, but we can keep looking. So H2O, again, has 2 lone pairs. We've seen many times that H2O can attack a carbon, so that's not going to be it. Nitrile, same thing. We've seen multiple times in SN1 and SN2 reactions that it can attack a carbon, so no. And then the last one is an amine. That's basic. Well, it's not really an amine, it's an NH2, but amine group, and it has a lone pair. So that also is going to be a nucleophile. So the answer to multiple choice 15, like I said, is going to be B. Okay, so multiple choice 16 asks, which will not have any effect on the SN1 reaction rate? So the first thing you want to do in these situations is go through in your head and figure out the different characteristics of an SN1 reaction, like the rate law, what kind of alkyl halides it prefers, what kind of nucleophile it prefers, solvent, and the product stereochem. So I'll give you a couple of seconds to take your time and do that, although you should have already done it by now. Okay, so the SN1 reaction rate is unimolecular, which means it only depends on the concentration of one thing, and in this case, that's the substrate. So the rate law is going to look like this. That means the concentration of the nucleophile will not affect the rate of the reaction at all. The type of alkyl halide that it prefers is tertiary or secondary. It prefers weak nucleophiles and polar protic solvents. And it is our 2-step reaction with the carbocation intermediate. So that means you have a mix of retention product and inversion product. Mix of products. So keeping all of these things in mind, we can go ahead and look at our answer choices. So which of the ones will not have any effect? A says primary, secondary, or tertiary substrate. That does have an effect because primary is very, very unfavorable for SN1. So you can go ahead and cross out A. Looking at B, a weakly basic leaving group. Since the SN1 reaction mechanism requires the leaving group to leave on its own, you actually need a highly basic leaving group or a good leaving group for an SN1 reaction. So B is not correct. C, the high concentration of the nucleophile. Well, we just wrote our rate law and that it only depends on the substrate. So having a high concentration of the nucleophile does not matter at all because it only depends on how much substrate you have available. Okay? Now, if you had no nucleophile, that would be a different story, but high concentration of the nucleophile will not make a difference. Polar protic solvent will have an effect. You need that. And temperature has an effect on every reaction, so that's not it. So the answer to 16 is going to be C. Okay, so multiple choice 17 asks which reaction generates the major product shown. So NBS over CH2Cl2 will actually add the Br allylic to the double bond if there's a double bond present. I know earlier in this mock we did it on an alkane, but in the presence of an alkene, it's going to add allylic, which means one space over. So instead of having the Br adding directly onto the double bond, you would have had these products instead in the correct answer, if this was the correct answer. It would either be this, well, keeping the double bond there because it doesn't interfere with the double bond at all. This or this could have all been potential products for that. However, that was not the answer given, so A is not the right one, but I'll write that down. NBS in presence of alkene adds Br allylic to double bond. It does not interfere with the double bond at all. So the double bond should be in the reagent and in the product. Okay. So hopefully you guys get that down. I'm going to move along. Okay, so looking at B, we have the same situation where the NBS is being added to... Oh, okay, wait, I'm sorry. So we have the same situation where the NBS is being added to the ring, and in this case, the BR actually is being added allylic to the double bond because it's being added one space or one carbon. Well, could you say one carbon away? Yeah, one carbon away. So moving over one carbon, then you add the BR. So that actually is the right answer, and the BR does prefer to be in the more highly substituted place. So this is not only the right answer, but the most ideal answer for NBS. So B is going to be the answer to 17, but we can keep going. C is going to be incorrect because when you add the NBS, not only are you adding it to the spot where the double bond was on, you're actually getting rid of the double bond in the product. So this is completely wrong. And then D is the chlorination of a ring. But the issue here is in order to do Cl2 over HV and add the Cl, you need to have a chained hydrogen present. So what I mean is you would have to have an open chain hydrogen to do the radical chlorination. So in this case, what the product should have looked like is this. You wouldn't be able to add the Cl directly onto the ring in this case because you're not using NBS. If you were using NBS, you could add the BR directly to the ring, but there's no case where you can add the Cl directly to the ring. It needs to have a free hydrogen from a methyl or an ethyl or whatever. So D is not the answer, and E is not the answer because although this is one of the products that can occur from radical bromination, it's not the major product because the question does ask for the major product. BR, as he mentioned during lecture, it prefers to have more highly substituted. So radical bromination prefers more highly substituted carbons. So had it added here or here, that would have been the right answer, but because it added terminal, that's actually going to be one of the minor products. He made the point of telling you that that doesn't affect Cl as much, that the rates for Cl are all very similar depending on, like, no matter if it's tertiary, secondary, primary, Cl will add to all of them pretty similarly, but BR, there's a large disparity between adding tertiary and secondary and primary. Much, much more favored towards tertiary or secondary. So I'll write Cl does not care as much. Because there's a little bit of a preference, but it's so insignificant that you wouldn't say, oh, like, it's impacting that major product or not. So E is not the answer because this is a minor product. So the answer to multiple choice 17, like I said, is going to be B. Okay, multiple choice 18 was the exact same question from before. I just wanted to show you that he chose to put it not only on his 2017 final exam, but also his 2016 final exam. So he's probably going to ask you something similar on your own final exam, especially because yours is way more multiple choice than it was in the past years. So point of me including this question again was basically that you guys remember to brush up on your naming. But just a reminder, the answer was D. Okay, multiple choice 19 was another question that we had done before, but again, this is how I used to take my exams, and I know the large majority of you don't actually look at the old exams that I post on Sakai, so I like for you guys to understand which questions are being reused multiple times, because when I would study for this class, I would also sit there and do every single exam, even if I had seen the questions before, because if he likes to reuse that question, it's probably because he's going to do it again. So again, just a reminder, the answer to multiple choice 19 was D. And if you want to scroll back, like maybe 10 minutes or so, the answer, or like the reasoning behind it, was up there. Okay, so multiple choice 20 was kind of a tricky one. You had to make sure you looked out for diastereomers because those are a type of isomer, okay? So the answer was 9. I'll go ahead and fill it in, and I will give you the 9 different isomers. So number 1 is going to be 1 ethyl, 1 chloro, cyclohexane. So that's going to look like this. Number 2, let me erase that. I'll write that a little neater. Number 2 is going to be cis, 1 ethyl, 1 ethyl, 2 chloro, cyclohexane, okay, just checking my spelling. So that's going to look like this. Okay. Number 3 is going to be trans, 1 ethyl, 2 chloro, cyclohexane. And that is going to look like this. Then number 4 is going to be cis, 1 ethyl, 3 chloro, oh my goodness, I'm a mess. Cyclohexane. Cis 1 ethyl, 3 chloro, cyclohexane. Okay, good. One, two, three. Okay. I'm going to erase and then give you the others. Okay, so number 5 is going to be trans, 1 ethyl, 3 chloro, cyclohexane. I'm running out of space. And that's going to look like this. Okay. Number 6 is going to be cis, 1 ethyl. I think, in my opinion, naming helped me get through these, so I recommend it. If you don't want to do that, that's okay though. 4 chloro, cyclohexane, So, and that's going to look like this. 1, 2, 3, 4. Oh, oops, I said cis, my bad. Okay, and then I'm going to erase and give you 7, 8, and 9. Okay, 7 is trans, 1 ethyl, 4 chloro, cyclohexane. I'm just going to abbreviate it with ... because you guys know what I'm talking about by now. Okay, and that looks like that. And then number 8 is going to be 1,1-chloroethyl. Oops. Cyclohexane. And that is going to look like this. Okay. In that case, you're not going to have a diastereomer because it's terminal. And then finally, number 9 is going to be 1,2-chloro. Oopsie. Ethyl cyclohexane. And that's going to look like this. Alrighty, and those are the 9 different isomers. Hopefully you got that, and if you didn't, please feel free to message me if you need extra help or like extra explanation, because I feel like this one will come up again. Or if you want, just memorize the answer. Okay, so multiple choice 21 says which statement is most accurate. So most of these are just memorizing, and the answer to this one is going to be B, but really quickly, the ones that I can debunk right off the bat: C, pi bonds add more to the strength of multiple bonds than S bonds do. That's not true. S bonds are actually the stronger ones, although once you're adding more bonds and you're getting more S character, that's what gives you the strength. D, pi molecular orbitals distribute maximum electron density. No, it's the sigma bonds that do. Triple carbon-carbon bonds are comprised of 1 pi and 2 sigma. No, obviously it's 1 sigma and 2 pi. And yeah, I think the number of bonding molecular orbitals is equal to half the number of atomic orbitals which combine to form them. Don't quote me on that because that's exam 1 material. And honestly, it's not that important. He never tests it. I would just memorize this question because this is the only thing that I've ever seen him ask about molecular orbital theory. And it just makes sense that the combination of orbitals in phase results in a bond, because if it's out of phase, we've always seen that there's repulsion, and in phase is the bond formation. Even with the Diels-Alder, for example, they have to be in phase when they come together, the diene and the dienophile. So this one slides underneath in phase, and that's how you get the formation of a bond. So the answer to multiple choice 21 is B, and this is definitely one I would write down because the conceptual ones are ones he doesn't really get creative with. Okay, so multiple choice 22 asks which of the following compounds can exist as diastereomers. And all this question is really asking is which of the following have 2 chiral centers, 2 distinct chiral centers. So what you're going to want to do is draw them all out and try to see if you can assign priority and if it's attached to 4 unique groups. So starting with number 1, butane is 4 carbons, MEPB 4, and then you're going to have 2, 3 dibromo. So now you're going to pick any of the carbons. Well, you have to really look at both carbons and figure out if they're attached to 4 unique groups. So this carbon is attached to a Br, the rest of the chain, a methyl, and a hydrogen. Same thing with the other one, a Br, the rest of the chain, a methyl, and a hydrogen. So they're both bonded to 4 unique groups, which means these are both chiral centers, and that means that number 1 can exist as a diastereomer. So what I would do if I was taking this exam is I would cross off anything that doesn't have 1 in it because I know 1 is going to be in the correct answer. Okay, moving on to number 2, it's cis-1,4-dichlorocyclohexane. So you want to draw your cyclohexane, 1, 2, 3, 4, cis. So the situation here is you can't assign priority because these chains are identical to each other. So you can't rank them. So that means although it can, like, sometimes they'll draw it with a wedge and a dash, these are not chiral centers because they're bonded to things that are equal on both sides. So it's bonded to one Cl, one H, and two chains that are identical. So 2 is not the answer. You can eliminate any of the answers with 2, and that's A, and that leaves you with D as the correct answer. But I'll draw the other ones out just to convince you guys. So 3 is going to be 3-chlorocyclopentanol. So pent being 5, OH is going to be on number 1, and then 1, 2, 3, 3-chloro. So in this case, what am I missing? Oh, okay, yeah, all right, never mind, my bad. So you can give them any stereochem. Actually, it's better not to give it because they didn't say cis or trans, so let's just keep it true to what they said. So on this carbon here, it's bonded to an OH, a side chain that is not equal to this side chain because this one separates at a Cl first. This has the point of distinction here, whereas it takes longer on the other side to reach that point. So the two side chains connected to this carbon are not identical. Hopefully we see that, which means that you can assign priority. So looking at this carbon, OH is 1, the side chain on the right is 2, and the side chain on the left is 3, and obviously the H is 4. Boop. Looking at the Cl is going to be number 1, the side chain, I guess, to the right is going to be 2, the side chain to the left is 3, and then the H is going to be 4. So these are both chiral centers, and that means number 3 can exist as diastereomer, which again matches our answer for D. So now we can try number 4 if we want to be really thorough. So 4 is 1,2-dihydroxypropane. So prop meaning 3, 1,3-dihydroxy. Dihydroxy is another way of saying 2 alcohols in it. So 1,3-dihydroxypropane. Since the OHs are terminal, they're going to be bonded to 2 H's, both of them. So that means they're not bonded to 4 unique groups, so 4 is not going to be a compound that can exist as a diastereomer, because they are not. Okay, so there was actually a mistake with number 5 when I was transferring it over. It's actually supposed to be 2,3-dihydroxypentane, so that's on me. I apologize. It's supposed to be 2,3-dihydroxypentane. So I'm sorry if that confused you because I could see why that would be an issue. So pentane, MEPB, 1, 2, 3. Okay, so 2,3-dihydroxy. So you're going to put an OH on 2 and then an OH on 3. And you could see that they're bonded to unique groups because you have off of this carbon, 1 OH, the rest of the chain, and a carbon. And then on this one, you have the OH coming off. This side of the chain is different than this side, and an H. So I completely apologize about multiple choice 22. It's supposed to be 2,3-dihydroxypentane, not 1,3. But that gives you the answer D for this question. Okay, so multiple choice 23 asks, which of the following substances reacts most rapidly with terbutoxide? And when you're thinking about the mechanism of terbutoxide or TBOC, the big bulky base is going to pull off a terminal hydrogen, and that will create the double bond that will kick out the Br. So you need to have a terminal hydrogen for T-butoxide to work properly. So keeping that in mind, you're going to want to look for the answer choice that's going to give you a terminal hydrogen that will kick off a Br. So starting with A, and you don't have a terminal hydrogen, you have secondary ones over here. So that's okay, but it's not the most favorable. Looking at B, you do have terminal hydrogens that can kick off. You actually have 2 methyls, so that gives you options. So B is looking really promising. C is a tertiary hydrogen, so that's very bad. You can eliminate C right off the bat because you know B is better. You can eliminate A because B is better. D, there are no hydrogens that T-butoxide is going to pull off because you can't really pull off a hydrogen from a benzene. It's very, very unfavorable. So that's not right. E, same situation. You're not going to pull a hydrogen off of a double bond. It's not going to happen. So the answer to 23 is B, because those hydrogens are most easy for the tert-butoxide to pull off. Multiple choice 4 asks, how many transition states and intermediates occur in the reaction shown below? The only thing about this multiple choice question is that the professor actually made a mistake in the product, and instead of a Br, it was actually supposed to be a CH3. So if you struggled with this question, that's probably why, and it's probably going to be a lot easier now. So if you want to pause and try it, I'm more than welcome you to do so, but I'm just going to carry on because this is a YouTube video. So whenever you see how many transition states and intermediates occur in this reaction, you're going to want to draw out the entire mech. So to figure out which kind of mech this is going to follow, you want to distinguish what kind of reaction it is. So you see Br is a good leaving group, and you see that you have a polar protic solvent, H2O, which can also act as a nucleophile. So most likely this is going to be an SN1 reaction. So let's get started with the mech, which I'm sure you have done a million times by now. The first step is going to be Br popping off, leaving a carbocation behind. And because a more stable carbocation can be formed in this situation, that there's going to be a hydride shift. So this H is going to shift. I'll do that in the next step though. Okay. Hydride shift. And that will give you your more stable carbocation intermediate. And then moving along, now your nucleophile, H2O, is going to attack. Oops. Okay. And for the last step, you're going to deprotonate your H2O because you don't want it to stay that way because H2O is a good leaving group, so it'll pop back off. You have to deprotonate it and turn it into OH. So another H2O is going to come in, or the Br, whatever, doesn't matter. It's going to come in and pull the H off. And then you're going to get your final product. H plus just means acid. It's the shorthand for H3O plus. Okay, so with this in mind, we can now look at the question and decide how many transition states are and how many intermediates there are. So transition states are going to be representative of each of the steps that you do in the reaction, and the intermediates are going to be the literal intermediates, so not the starting reagent or the ending product, but the intermediates in between your reactions. So each step, like I said, is going to be a transition state. So 1, 2, 3, 4. So right off the bat, you know that your answer is going to have 4 transition states, and the only answer with that is B. So B is going to be your right answer for number 4. But just to show you, here are your 3 intermediates, because these are not the starting material and these are not the ending. They're the intermediate. So multiple choice 25 asks, which is the correct rate equation for the reaction shown? So basically they're asking you, is this going to be an SN1 or an SN2 reaction? So looking at the fact that we have a strong anionic nucleophile, I hope we all remember that that is characteristic of an SN2 reaction. We have a polar aprotic solvent, again characteristic of an SN2 reaction. And we have a primary alkyl halide over here. Again, another characteristic of an SN2 reaction. So once you realize that this is an SN2, you have to make sure that you remember the rate law. And an easy way to remember it is if it's SN2, it depends on the concentration of 2 different things, being the alkyl halide and the nucleophile. SN1 depends on the concentration of one thing, which is only the alkyl halide. So I pretty much gave you the answer to this one. The rate is going to be B. Rate equals K times alkyl halide times the nucleophile. The little brackets just represent the concentration of, and K is the rate law constant. So yeah, multiple choice 25 is going to be B. So multiple choice 26, what is the pK of an acid at pH 5? Da, 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 da. This is the same question that we actually did again. I just, again, wanted to make the point that he used this question twice. So I genuinely would not be surprised if this was the exact question on your final. But in case you guys don't remember, the answer was B. And you can scroll back in the video if you want the explanation for this. So multiple choice 27 asks, which of the alkanes shown below will produce only a pair of enantiomers of stereoisomers of one tertiary bromination product in light-induced radical bromination? Okay, so that's kind of a lot to start with. So light-induced radical bromination is the same thing as saying like bromination of an alkane in the presence of light. So the reaction overall usually looks like this. Hopefully that will help you guys recognize. This is actually going to be a type of substitution reaction. Okay, so what ends up happening in this reaction, oopsie, I forgot to write the light. So what ends up happening in this type of reaction is that the Br is going to replace an H. So I'll write that down. An H present on the molecule. And from the radical lecture, we remember, sorry, I was about to sneeze. From the radical lecture, we remember that Br actually has a little bit of regioselectivity with its replacement. So Br in particular prefers to replace tertiary hydrogens. So an example of a tertiary hydrogen would be this. A secondary hydrogen would look like these, and a primary hydrogen would be any terminal carbon. Okay. So with that in mind, we have to now think about how would we get only a pair of enantiomers. So the trick here is that you have to have a product that when brominated is going to give you one chiral center, not two. Okay? Okay, so what you're going to want to do is you're going to want to look for a compound that's going to give you one product. So that means it has to only have one tertiary hydrogen, and that will give you a chiral center from that product, okay? So, and one chiral center only in the compound. So looking at A, there are two tertiary hydrogens. One is here and one is here. So that means the Br can add to either one of these, and that will give you a mix of products, and you only want one enantiomer pair. Here you would get two enantiomer pairs because you can have the Br add here on a wedge or a dash, or you could have the Br add here on a wedge or a dash. So A is out. Looking at B, we again have the same issue where we have multiple tertiary hydrogens. So the Br can add to any of these and give you a mixture of products. Also, if the Br were to add to this one, it actually would not be a chiral center because we would have the same thing on both sides of the ring. So that also eliminates B. You would have too many products, not one single enantiomer pair. Okay, C. Again, we have the same issue with multiple tertiary H's And actually, if you add the Br to any of these H's, you're still not going to get a chiral center. For example, say I add the Br, say I add the Br here, this carbon is still bonded to 2 methyls, so that means this is not chiral because it's not 4 unique groups. If you want to add it to the one in the middle, it's bonded to 3 isopropyl groups, so not chiral. Alrighty, looking at D, we see we only have 1 tertiary hydrogen, which means that we're only going to get 1 spot the Br can add. Now we have to make sure if after we add the Br, it's going to be a chiral center. So let's erase, add the Br, and see if these are 4 unique groups. So you have 1 unique group, the Br, 2, the second unique group is the methyl, the third unique group is the chain on the left, and then the 4th unique group is the ethyl, or the chain on the right. So that means this will be a chiral center, and the Br can add on both a wedge or a dash. So you'll only get 1 product that's a pair of enantiomers. Technically 2 products, because you'll get the Br and the wedge and the dash, but 1 chiral center in your product. So D is going to give you the pair of enantiomers from 1 product. Okay, looking at E, just to make sure, we have the exact same situation as C, just a little bit smaller. You have multiple tertiary hydrogens, and even if you add the Br to any of these, none of them would be chiral centers because they're not bonded to unique groups. For example, this is the same as this. If you added it here, this methyl is the same as this methyl. So the only one that would give you an enantiomer from 1 chiral center is going to be D. You can compare A and D because the reason A didn't work is because Br could add here or here because it had 2 tertiary hydrogens. D, they eliminated that by adding an extra methyl. So there was only 1 tertiary hydrogen that the Br can add to, hence only 1 pair of enantiomers. Okay. Since you guys learned radical bromination relatively recently, I think it might be worth going over the mechanism in the context of this problem. So I'm going to use the starting material from the original answer choice D and go ahead and go through the mech. If you feel comfortable with the mech and you don't want to go through it, feel free to skip this part. I just feel like it might be useful for some people. So radical bromination mechanism. So the first step, step 1, is referred to as the initiation step. And this is where you get the formation of your radical Br. Okay. So you start with Br2. In the presence of light, which is the same as HV. And what happens is that the bond separates in half, where 1 electron goes to the left Br and 1 electron goes to the right Br. It's very important to note that the half arrow is the movement of 1 single electron, not both. Okay? So then you end up with 2 Br radicals. Okay. I'll just erase. Okie dokie. So step 2 is the propagation step, and this has 2 parts. So step 2, propagation, and then in parentheses has 2 parts to it. Okay, so part 1 is going to be the Br radical interacting with the tertiary hydrogen of choice. in our question's case. It could also be a secondary hydrogen or a primary. Those are just less favorable, but they do happen. So I'm going to draw out the compound that we started with. Okay. And then the radical Br. So, oops, I forgot to draw in my hydrogen. Okay, so that's our tertiary hydrogen of choice. So what's going to happen is that one electron from this bond is going to move back onto this carbon. One electron from this bond is going to come, and form the new bond with the radical Br. And this radical is also going to come to form that bond. Sorry, I had to sneeze. I have really bad allergies today. Alrighty. So, the product is going to look like this. Okay. And then you're also going to have the formation of HBr. So that's part 1 of the propagation step. Part 2 is going to be the radical on the on the chain that we just created interacting directly with another Br2 in solution. Okay, so instead of having one electron go to both BRs, you're going to have one electron go to one BR, and the other one is going to go directly to, well, technically it does go to that BR, and then it goes to the electron or the radical here, but for the sake of saving a step, you just draw it directly to the radical. Okay. And this is going to be the addition of the Br to our chain. So now you have this Br over here that added directly to the chain. And then you're also going to have one Br radical as a result. Okay. Okay, so step 3, the final step, is called termination. And this is the one that he usually doesn't focus on very much, but it's still good to know because you just never know when he might ask. Reason why he doesn't focus on this as much is because this is when you have to add the radicals together in all the ways possible. And I'll give you like 4 usual ways that they're going to add together and then show you in the context of this. But it gets kind of tedious and repetitive. And it's also just a lot of work for one step of a reaction. So a lot of times he'll leave this out. But like I was saying, step 3, you add all radicals together in all ways possible. Technically, there is one where you're adding a radical with a non-radical, but this is my definition. This is how I remembered it, and this is what made it easy for me. So these are the 4 ways that they'll usually add together, and I'll show you in context of an example. So, number 1 is that both radical alkanes formed can be added together. So, for example, I'm going to do this not with ours because ours is very complex. It's a very large one, but I'll give you an example, right? Say this was the alkane that was formed, the radical alkane. You can add it to its exact same self, like this, and that would give you this as one of your termination products. I'll try to do it in the context of ours, but it might be a little complicated because ours is very big. Let me make sure that's the same. Okay, so it would be this plus another one. They would come together like yeah, this is gonna be a little wild for ours. You get the picture. Basically, they're gonna make a giant bond there that I don't feel like drawing out. I'll try. Okay. So on one side, it's going to be 1, 2, 3, 1, 2, 3. Okay. If you want to skip over this, feel free. I'm just being anal in case someone wants to know. 1, 2, 1, 2. Okay, so that's what it would look like for ours, but he wouldn't ask you, he wouldn't ask you with such a complex product. But as long as you get the picture, you add the two radicals together. Okay. The second way that you can add radicals together is by adding the radical, oops, let me do that in the same color. Add the radical alkane formed plus your radical halide, or to your radical halide. So, using the example from before, say we did this. They would add like so, and you would get that. For ours, it would be exactly what we did. You just add the Br to the radical. Okay. For ours, it would look, I definitely missed a carbon. Oh no, I didn't. Did I? No. It would look like this. Okay. So the next way you can add them together is adding the two radical halides to each other. Add two radical halides to each other. So, for example, you generate multiple radical BRs in your reaction. So all you have to do is just add them together. And that will give you Br2. Okay. And last but not least, you're going to add let me write it like this. Add two radical alkanes to each other, but, so that's the same as number one, but with the formation of a double bond in your product. I might have to move this up a little bit. Okay. Okay. So, for example, using the less complex one, oops, let me give more space. So you're going to incorporate a terminal hydrogen from one of them, or not a terminal hydrogen, but one that's next to the radical, right? So the way it's going to form is like this. So one of the electrons from this hydrogen is going to form a bond with this radical, and then one of the electrons is going to form a bond with this radical to create a double bond. Therefore, you get rid of both the radicals. So then you end up with the H here, and then you end up with a double bond here. So if this is A product. If this is B product. So those are the 4 ways that you can terminate a radical bromination. Multiple choice 28 asks, which is the molecular formula of a hydrocarbon having 10 carbons with 4 pi bonds and 1 ring? So the first thing you have to do is figure out how much an unsaturated, or one without any pi bonds and no rings, chain would be. And the way you do that is using this formula. So CnH2n plus 2. And this will tell you how many hydrogens there's supposed to be. So in this case, we have 10 carbons, so C10, H 2 times 10 plus 2. So it's supposed to be without pi bonds and a ring, C10, H22. Now, the important thing to note is that each pi bond, which is a double bond, is equivalent to subtracting 2 hydrogens. Because when you have a double bond, you take a hydrogen from both carbons. So what would normally be CH3 in a single bond becomes CH2. Rings are going to be the same thing. Every time you do a ring, you're going to subtract 2 hydrogens. So with this in mind, we now can multiply. So we have to take 4 pi bonds. So 4 times 2 equals 8. Ignore my dog snoring in the background violently. And then we have 1 ring. So 1 times 2 equals 2. And that's 10 hydrogens that we have to subtract in total. Oops. Okay. So now, if what we were supposed to have is C10H22, and we have to subtract 10 hydrogens, you end up with C10H12, and that's going to be answer choice A for multiple choice 28. Okay. So the first thing you're going to want to do for multiple choice 29 is, since they're asking you the smallest bond angle, you want to draw out the structures of each of these and hopefully remember their shapes and the corresponding angles for each of the shapes. So NH4 is going to look like this. And this is going to be a tetrahedral shape. Let me write this a little neater. Okay, so this is considered a tetrahedral, and tetrahedrals have a bond angle of 109.5 degrees. Now looking at CH3 plus, it is going to look like this. And this is going to be a trigonal planar molecule with a bond angle of 180 degrees. Then regular NH3, or ammonia, is going to look like, whoops, this. And this is going to be a trigonal, pyramidal, with a bond angle of about 107 degrees. Okay. And then H2O is going to look like, oopsie, no. This, and this is going to be considered V-shaped or bent. And this is going to have a bond angle of 104.5 degrees. And then finally, what was our last one? CO2. And that's going to look like this. Oops, not like that. And this is going to be a linear geometry. And it's going to have a bond angle of 180 degrees. So all things considered, the smallest bond angle you're going to find is in the V-shaped or bent molecule of water. So the answer to multiple choice 29 is D, H2O. Multiple choice 6 asks, which compound would have the most endothermic heat of formation, which is represented by delta G of F. So when you're thinking of heat of formation, the least stable a molecule is, the higher the heat of formation is going to be, or the more endothermic the heat of formation is going to be, because it needs a lot more energy to form unstable bonds. So I'm going to write that down. The least stable molecules have the highest heat, or most endothermic, I should say. The most endothermic heats of formation because it takes more energy, which we all know heat is a form of energy, to form unstable bonds. So all this question is really asking us is which of these molecules is the least stable, and as you guys can probably figure out very easily, it's going to be C, because even 4-membered rings are unstable, 3-membered rings are almost unheard of. So the answer to multiple choice 6 is going to be C. Okay, so multiple choice 31 asks us to rank the indicated bonds in order of decreasing bond length, the longest first and the shortest last. So as I mentioned to you guys before, single bonds, between carbons are going to be longer than double bonds. I'm talking about length here, strictly length, are going to be longer than double bonds. And then triple bonds are going to be the shortest. Keeping that in mind, then CH bonds are shorter than any CC bond. Okay, so now I'm going to erase, and we can look at our different answer choices. So number 2, right off the bat, is going to be a single CH3 bond. So looking at the others, that's going to already be our longest one because it's not a CH bond, it's a CH3 bond, and it's a single bond, so it's the longest of the CH3 bonds. So now you're going to want 2 in the front if the longest is going to go first, so you can eliminate anything where 2 isn't the first, which is A, E, and D. So now you only have B and C. Our next longest is going to be our other carbon-carbon bond, which is a alkene in number 1. So both B and C have 2 first and then 1 second, so that's good. Now you're comparing a CH3H bond and a CH2CH bond. So I'll highlight the bonds in question. So this one is not one that they generally teach you. You kind of have to reason through it, but now that you've seen this on an exam, you can remember it for the future. But the reason why number 4 is going to be shorter than 3 is because of opposite charges attract. There we go. So because you have all of this, oopsie, let me do this in a different color. Because you have all of this high electron density from the double bond, that's actually going to pull the proton, because obviously an H is a proton, closer to it, decreasing the bond length. So this is going to be closer than this would because this is a single bond carbon. Okay, so the answer for this one is going to be C. Just keep in mind if there's high regions of electron density nearby, that's going to shorten nearby CH bonds because it's going to pull the H closer. Okay. Multiple choice 32 asks, which compound releases the least energy when undergoing combustion? So when you're thinking about something that's going to release the least energy, they're also asking you which one is the most stable. So it releases least energy equals which compound is more stable. So, in general, when you're comparing alkanes of the same size, and the first thing I did when I saw this question is I counted the number of carbons in all of them. They are all 7 carbons long. Okay, back to what I was saying. So when you're comparing alkanes of the same size, increased branching is going to increase stability. Now, this is kind of an area of debate as to why it increases the stability. Personally, I think it's because the van der Waals of a branched alkane, like these carbons, these methyls, can interact with each other. But according to Google, in case you guys were curious, it means that the compound is more compact, and this decreases molecular surface area per atom, which apparently leads to a lowering of energy and an increase of stability. But this is still something apparently that chemists are debating. But just know that in general, increased branching of an alkane is going to lead to increased stability. Also, the smaller it is, as long as this is an open compound and not a ring, in general, the more stable it's going to be. So when you're comparing just ones of the same size, you're going to look for the one that's the most branched. And in multiple choice 32, the most branching occurred in answer B. Answer B. Okay, multiple choice 33 is another one he's repeated on not only 2 finals, but also on midterms, as we've seen from exam 3 pre-mocks and mocks. But again, the answer is going to be B, because carboxylics are going to be your most acidic, and every time you add a halide, that's going to increase the inductive effect, which makes a compound more acidic. So 2, the carboxylic acid with the Cl is going to be more acidic than 5. And then the alcohol is going to come next, and then the amine, and then the carbon, or CH4, because carbons never want to lose their H's. If you want the full explanation, you can go back to the other question, but we already did this now 3 times. So yeah, the answer to multiple choice 33 is B. Multiple choice 34 says, left to right, what are the stereochemical configurations of the compounds shown? Okay, so starting with number 1, the first thing you're going to want to do is rank the priority. So obviously halogens are going to be number 1, so Br is 1. And now you're comparing a CH2CH3 with a regular CH3. And because the CH2CH3 is heavier, that's going to be number 2. Then the CH3 is going to be last. In this case, you have your H on a wedge, so that means whatever you get, you have to switch it. So 1, 2, 3. So that means it's R, but because we're switching it, it's going to be S. So now you can look at your answer choices and eliminate anything where 1 is R, and that's only C. So it helps, but it's not much. Moving on to 2, alcohol is going to have the highest priority because it goes halogens, then alcohol, well, carboxylics, and then alcohols because you want the highest O character first. Okay, so O is going to be number 1, and then you're comparing a C, CH2, CH3, CH2, CH3, my bad, versus a CH3 with or CH with 2 methyls coming off of it. So this is what these would look like. Okay, so because this one is bigger, this one's going to be number 2, and this one is smaller, so it's going to be 3. So then you can go 1, 2, 3, and because your lowest priority is on the dash, which is the H, you can keep this as S, which it is because it's counterclockwise. Looking at number 3, again, halogen's going to come first, so Cl is 1. Then you're going to be comparing the CO, or like the OCH3, like the ether, and then the methyl. So the ether is going to come second, and the methyl is going to come last. 1, 2, 3. Because your lowest priority is on a dash, you can keep that as R. So now looking at our answer choices, we want SSR, and that corresponds to B. So the answer to multiple choice 34 is B. And I think number 3 brings up a good point that although O character is important, it is not as important as the halogens. Multiple choice 35 asks, which of the following are diastereomers? So a diastereomer, or a pair of diastereomers, for one thing, it has to be 2 different compounds. So you could actually eliminate any where there's 3, because it's 2 different compounds where one of the stereocenters is the same and one of the stereocenters is different. So now what you want to do is just go through each one and assign all of the configurations, and then from there, you could figure out which pair has one stereocenter the same and which one has one different. Okay, so you do actually have to reference the answer choices. You can't just do this right off of your head. Alrighty, so looking at number 1, I'm going to start with the carbon on the left, or the chiral center on the left. The OH is going to be the first priority because alcohols come before carbons. Then the rest of the chain on your right, and then the methyl on your left. So going in order, 1, 2, 3, you're going to get R, because it's a clockwise rotation, and because your lowest priority H is on the dash, you don't have to flip it. Looking at the one on the right, or the chiral center on the right, the halogen is going to be number 1, then the rest of the chain on your left, and then the rest of your chain on your right. Because your lowest priority is on a wedge, no matter what you get, you have to flip it, because your lowest priority is the CH3. So 1, 2, 3, you get R, but it's actually S. So now on the side, I'm going to write that 1 is RS. Okay, moving on to number 2. I'm going to look at the chiral center on the left first. OH is going to be the highest priority. It's going to be the same ranking as before, so I'm not going to go through it. The only difference is that because your H is now on a wedge, whatever you get here, you have to flip. So we get R, but it's actually S. Looking at the chiral center on the right, we're going to have the same priorities. The halogen is going to come first. The rest of your chain on... Oops, let me do this in a separate color. Halogen first, the rest of your chain on your left, and the rest of your chain on your right. In this case, again, your lowest priority is on the wedge, so you have to flip whatever you get. So it's R, but once again, it's going to be S. So now on the side, I'm going to write that number 2 was SS. Moving down to number 3, same priority again. OH is first, rest of the chain on the right, and methyl on the left. In this case, your lowest priority, your H, is on the dash, so you don't have to flip it. So going in your clockwise motion, you get R. Moving to the one on the right, Cl first, rest of the chain on the left, rest of the chain on the right. Your carbon is going to be your lowest priority. That's on a dash, so you don't have to flip it. So you get a clockwise rotation of R. Moving over, I'm going to write that compound 3 was R, R. Oh my god, I can't write. Okay, looking at number 4, starting with the one on the left. OH first, rest of the chain on the right, methyl on the left. Because your H is on a wedge and that's your lowest priority, you're going to have to flip whatever you get. So you get R, but you actually get S. Okay, looking at the stereocenter on the right, Cl is first, rest of the chain on the left, rest of the chain on the right. Because your carbon is the lowest priority and that is on the dash, whatever you get, you keep. And in this case, it is R. So now we could write that number 4 was SR. Okay, now we can look at the answer choices and see if the ones that they give us are diastereomers. So A says 1 and 4. 1 is RS and 4 is SR. So in that case, both of the stereocenters changed, and these would actually be enantiomers. For a diastereomer, only one of the stereocenters has to change. So A is not it. Looking at C, we have 2 and 3. So 2 is SS and 3 is RR. Again, both of these changed, both of the stereocenters changed, so you have another pair of enantiomers. Finally, looking at D, 1 and 4, you have RS, and then you have SR. Oh, I'm so stupid. I was looking at the wrong thing. Okay, D, 1 and 2, you have RS and then SS. So the first stereocenter switched from R to S, but the second stereocenter is still an S. So D is the correct answer because you have RS and SS. One stereocenter the same, one stereocenter has changed. That is the definition of a pair of diastereomers. So in this case, you actually had to reference the answer choices when you were answering the question, or you wouldn't have been able to do it on your own. And the answer to multiple choice 35 is D. Okay, so multiple choice 36 is one of the weird, abnormal reactions from the alkynes chapter. So normally when you treat things with HBr, say it was a triple bond and you treated it with 1 mole of HBr. If you treat with 1 mole HBr, you're going to get, oops, let me count the carbons. 1, 2, 3, 4, 5, 6. 6. So, oops, I'm missing methyls. You would get a Br added anti across the triple bond with the double bond still there. And we've seen before that if you treat a double bond with HBr, you get rid of the bond and add Br to either side of the bond. However, 2 moles of HBr with a triple bond is kind of an interesting case because instead of getting the Brs added across the triple bond, you're going to get this instead. Give me 1 second. 2 HBr. Oops, I made it too long. You're going to get the Brs added either both on the left side or both on the right side with no bonds remaining. So I will just add them arbitrarily here. And hopefully you guys added this to your reaction sheet when I mentioned that during the alkynes chapter, and that would make this question really, really easy. So the only answer that matches the one that I just got is going to be E. Multiple choice 37 asks us to rank the following alkenes in order of increasing heat of hydrogenation, least exothermic first and most exothermic last. So hopefully you guys recognize this question because it has come up before a couple times. So when you're thinking of increasing heat of hydrogenation, least exothermic are going to be the most stable double bonds, and most exothermic are going to be the least stable double bonds. Just a reminder, stability of double bonds goes by the following two rules in order of increasing priority. So the most important thing is how highly substituted the double bond is. So the more carbons that are coming off of the double bond or substituents, the more stable that double bond is going to be. Then the second most important is that Z alkenes are less stable than E alkenes. So if you're comparing two alkenes that are the same level of substituted, like say they both have two carbons coming off and two H's, the one that is going to be an E alkene or a trans alkene is more stable than the Z alkene or the cis alkene. With that in mind, let's go ahead and look for our most highly substituted double bond. And starting with number 1, we have carbons coming off on all sides, so that's a good sign. 2 has 2 carbons and 2 hydrogens. 3 has 3 hydrogens coming off. 5 has 1 hydrogen coming off. And 4 has 2 hydrogens coming off. So right off the bat, you know that number 1 is going to be your least exothermic because it's the most stable. And then since 5 is the only one with 1 hydrogen on it, 5 is going to come next. So you can eliminate any of the answer choices that aren't 1, 5 as the first two. So you can eliminate B and D. Now you want to compare the ones that have 2 hydrogens on it because those are the next most stable. So between molecule 2 and molecule 4, the only difference is that 4 is going to be a Z alkene because the hydrogens are on the same side of the double bond. They're both going down. And the higher priority or the carbon chains are both up. So they're both on the same side of the alkene. So that one is going to be less stable than number 2 because number 2 is an E alkene because the hydrogens are opposite of each other. Hopefully when you see these side by side, you can see that these two are next to each other and these two are opposite each other. Okay? So 2 is going to come next and then 4. So you can eliminate any, where is that? So you can eliminate any where 4 comes before 2. So you can eliminate C. And now 3 is going to be your least stable because it has 3 hydrogens on it and it's the only one that has 3 hydrogens on it. So 3 is going to come last. With that in mind, A is going to be your answer. Oops. Okay. So for multiple choice 9, the question asks, which set of reagents will yield the same product with each of the alkenes shown? So they're asking which reagents, A, B, C, D, or E, can react with both of these alkenes and give you the same product. So the first thing you want to do is make sure you know how all of these reagents function. I think the only mech I haven't given you guys was the HBr over CH2Cl2 mech. So I'll give you in words what this does first. So protonates, the less substituted end of the double bond, and it leaves behind a carbocation. Leaves, I'm going to just say positive, but you guys should know that that's a carbocation. And then the Br anion attacks the carbocation. In these reactions, there is the possibility for a shift. Anytime you have a carbocation, you're going to have the possibility of a shift. So for example, we'll do it with the first one. Oops. you know what, I'm going to, actually, we'll draw it the same way. So plus HBr. The electrons are going to pick up the H. The H is now added here, leaving a carbocation here. And then the Br, the Br anion, actually in this case, there's going to be a shift. So you're going to have a hydride shift from here over. Okay. So now the more substituted carbocation is made, and the Br is going to attack there, giving you this product. Okay, so that is the answer for that how do I word this? That is the product that HBr makes when it attacks the first alkene. So it's important to keep your notes organized with this because it can get very, very messy. So I'm going to erase. Okay. So A plus 1 equals this. Now we can move on to A plus the second one. So treat it with HBr. The H is going to protonate the terminal end of the double bond. Leaving the carbocation here. In this case, you're not going to have a shift because the more stable carbocation is already formed. So now your Br anion is just going to come in and attack that carbocation. And that, my friends, is the same as this one. Okay, so we actually don't have to keep going because these are the exact same. If you don't believe me because it's like mirrored, you can name it and you'll get the exact same thing. So A is the answer to number 9, but we should go through and see what the other reagents at least do without drawing out all the mech because it takes a long time. Okay, why? Okay, so BH3 over THF as your first step, and your second step H2O2/OH. This is going to be your anti-Markovnikov addition of an OH with no rearrangements. So we've did this mechanism a couple times already with this, the notes, and the premock, but we'll do really quickly what would happen if you used this on A. Okay, so anti-Markovnikov basically just means you're going to add OH to the less substituted side, which normally doesn't happen. Usually you want your OH on the more substituted, so that's Markovnikov. Anti means you're adding it to the less substituted without any rearrangements. So in this case, your product would be like this if you used the first alkene. Using the second alkene, your product would look like this because your OH is going to add to your less substituted side, which for this one is here, and for this one it is here. And these are not the same product, so you know B is not going to be your answer. Okay. Alrighty. So moving on to letter C, Br2 over CCl4. This is going to be the addition, or I should say the anti-addition. I'll explain what that means in a second. The anti-addition of two BRs across a double bond. So anti just means that the two BRs are not going to have the same stereochemistry. So one BR is going to get added on a wedge and one of them is going to get added on a dash. Reason being is because when you have this double bond and it attacks the BR2, it forms a ring with one of the BRs, right? And then the second BR is going to come in and attack, opening up the ring. So what that does is that ensures that this BR and this BR are not going to have the same stereochemistry because this one's going to be coming from the top and this one is going to get pushed away underneath. I did do the mech for this in the pre-mock a million times, so I'm not going to bore you guys with it again. It's at this point you should be memorizing what the reagents do and what the products are going to look like without doing the mechs for everything. Okay. Also, if you're ever confused, you can always like Google BR2 over CCl4. It comes up really easily, or always text me. Like, I don't mind, but some people feel bad. Like, I don't know. Some people are shy, don't like to ask questions. But I personally really don't mind. You could always ask me anything, even if it sounds stupid. Okay. So the next one is BR2 over H2O. So this is another anti-addition of one BR and one OH. So the way that this one works is very similar to the last one. You're going to have the ring intermediate formed when the double bond attacks the BR. So it's going to look like this. And then the OH is going to come in, or the H2O. The H2O is going to come in and attack the more substituted side, whichever one that may be. So the OH attacks the more substituted side in this one, and they are going to be anti to each other because this OH is going to be coming from the top, and this BR is going to get pushed to the bottom. So the addition will always be anti, so they're always going to be trans to each other. And then the last step is just deprotonation of the H2O. So you just turn it into an OH. Again, I've done this mech a bajillion times. Please watch the pre-mock if you haven't already. But just so you get used to being able to say what the reagents do in your head without actually having to draw the whole mech. Okay. And the last one is oxymercuration. So give me 1 sec to erase. HgOAC2 over NaBH4. So this is going to give you the Markovnikov addition of an OH. So you're adding the OH to the more substituted side of the double bond without rearrangement. This one you don't, at least I've never seen O'Connor ask any questions about the mechanism for, so I wouldn't even worry about it. Just know what it does. So for example, if we treated the first alkene with, I'm just going to call it E because that's the answer choice, you're going to get this. Because it's the Markovnikov addition, so you're adding to the more substituted side, and there is no carbocation intermediate, so there's going to be no shift. So that is how to do number 9. That is what all the reagents do, and since we found out that the A gave you the answer right away, we didn't have to go in and do the rest. Okay. So multiple choice 39 asks, which of the following are electrophiles? So that means these things are going to want electrons. So electrophiles directly translates to electron loving. So in general, electrophiles are going to either have plus charges or they're going to have open orbitals, open/empty orbitals. Anything with a negative charge or lone pairs are nucleophiles. So with that in mind, we can eliminate 1, 3, 4, and 5 because these all have lone pairs, and 1, 3, 4 have negative charges. So these are not going to be your electrophiles. Now, number 6 has a plus charge, so you know that that's going to be one of your electrophiles. So you can eliminate any of the answer choices without 6 in it. Oops, not that. And you can eliminate anything with 1, 3, 4, or 5 in it. And that leaves you with B, but just so we can be really, really clear, you can look at the structure of BF3. BF3 is actually a Lewis acid, which means that it is a electron acceptor. The structure of BF3 actually has this empty orbital up here, so it can accept electrons, making it an electrophile. So the answer to multiple choice 39 is going to be B. But you didn't technically need to know that BF3 had an open orbital in order to answer the question if you knew that 1, 3, 4, and 5 are nucleophiles. Okay, so 1x says, using the example given, show the mechanism for the formation of the two possible products. Circle the path leading to the conjugate 1,4 product. Show all charges, lone pairs, and the movement of electrons with curved appropriate arrows. Okay, so since these double bonds are equivalent to each other, you don't have to compare the two and figure out which one will give you the more stable products because they're exactly the same. So you can actually just jump right into the mech in this situation. So I'm going to go ahead and start. So the first step is that the electrons are going to pull the H off from the HBr, and that these electrons are going to return to the Br. And this leaves you with this carbocation and the H now added onto it, and the Br anion. Okay, so now for the first one, you want to draw the the resonance. So the way that this resonates is this. Oops. Again, drawing the H is optional. Now using the two resonance forms, you're going to add the Br and figure out which one is the kinetic and which one is the thermodynamic product. So starting with this one and adding the Br. The Br is going to come and attach where the carbocation is. And this is going to give you the more highly substituted halogen. So this is going to be the kinetic product. Moving on to the other one. The Br is going to add to the carbocation at the end. And this is going to give you the more highly substituted double bond. So this is the thermodynamic product. Oops. This is also going to be the path that leads to the conjugate 1,4, because as you can see, the Br is on 1, 2, 3, and then the H is on 4. When they're talking about 1,4, they mean where does the Br and the H ends up. So you can go ahead and circle this one. Okay, moving on to part B. With the aid of the reaction coordinate diagram and specific examples, explain the effect of temperature on product of formation of the above reaction. For this one, I'm going to fill in exactly what O'Connor put, so that way you guys have the most accurate answer. So the kinetic diagram is going to look like this, where this is the thermo, and then this is the kinetic, the kinetic is going to have the smaller activation energy, but the higher finishing delta G, whereas the thermo is going to have the higher activation energy and the lower delta G because it has the more stable product, but it's harder to reach. Okay, so he says that, I'll do this in purple, the kinetic product is formed most rapidly. Oops. And then he gives the example of the kinetic product from the prior one with the more highly substituted halogen. The thermodynamic product is the most stable product because it has the more highly substituted double bond. And then again, he includes the example from before, also including that it has more substituted double bond because that's what makes it the more stable product. Moving on, he says that the kinetic product, or this product from before, is formed more rapidly because its formation has a lower activation of energy, or energy of activation, might be. I'm just going to abbreviate it as EA. And because it is from a more stable carbocation intermediate. I'm going to abbreviate intermediate as INT. It is also more fast. Okay, how do I explain this? He wrote it is also speeded, but that's not English. It also forms more rapidly because of the proximity effect. Finally, when the temperature of the system increases, the thermodynamic product is favored because it can meet or reach the higher EA. At low temps, the kinetic product is favored. And when they say favored, they mean it is more present, like it is the majority or like the major product. Oops. Okay, and that is the answer to... Okay, so this problem is one of the ones where it does make a difference if you draw the resonance or not. And I do it a little bit differently than O'Connor does, but using the tricks that I gave you, let me repeat the tricks really quickly. So if you have your diene and it goes out, you put it on a dash. If it goes in, it's on a wedge. If you have your dienophile and it goes in, it's on a dash. And if it goes out, it's on a wedge. Now, keeping that in mind, we can go ahead and draw the different resonances for these. So drawing the diene, you're going to have this kind of a resonance where the S is going to donate a lone pair, and that's going to pop this one up over here. Okay, and then for your aldehyde, it's a electron withdrawing group, so the electrons are going to move up towards the O, giving you the this. Now, what I do, and this has always worked for me, is whenever I want to get this anion to this carbocation, I flip the aldehyde. I flip the or like this whole compound, like, or I mirror it. I guess I can explain it as. I'll show you in a second, because that way it gets the plus sign closer to the negative charge, and that actually gives you the right answer if you use my trick from before. So when you're doing these, make sure you get the plus sign close to the negative charge. So here, I'll show you what I mean. No, that's not what I wanted to do. So when I say flip, I'll draw them how, actually no, I'll draw them in their resonance form. Okay. I do this. Because now you actually get this plus sign closer and it follows my trick better. And this will always work if you do it this way, but O'Connor does it a little bit differently. I just don't see how you get the answer from the way he does it, because he doesn't mirror it, but using my rule of, oh, in is on the dash and out is on the wedge, it doesn't work that way. So if you're going to use my rule, then you have to flip it so you get the plus sign physically as close as you can to the anion. Okay? So keeping this in mind, now you're going to have the SH coming off of the double bond. It's not going to have stereochem because it's sp2 carbon. So then the carbon over here is going to be up here, and it's going to be on a dash because it's going out. You could fill in the 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then the aldehyde is going to be coming off of 5, and because it's facing away from the diene, it's going to be on a wedge. And this is the right answer. This is just how I personally do it. If you guys have a different way of doing it, go for it. But if you're going to use my rule with like the, here, I'll show you again, just as a reminder. If you're going to use this little mnemonic thing, make sure you physically put the carbocation as close as you can to the anion. So that means in some cases you have to mirror it. Okay, so drawing it neatly, this is the product. Did I not put it on a wedge down here? Oops, I meant to put it on a wedge. But yeah, that's the answer to that one. Okay, so this is one of the special cases of the Diels-Alder, but O'Connor does like to go over it or include it in his exams quite often. So redrawing our starting materials, they're going to look like this. And you can go ahead and do your 1, 2, 3, 4, 5, 6. Where you know between 2 and 3 is going to be the formation of your new double bond. Okay, so these two carbons here are actually going to flip up and form a bridge between 1 and 4. Oh, oopsie, I didn't number it right. Skipped a carbon. But the numbering over here is correct. So these two are going to actually flip up and form a bridge between 1 and 4. So you can go ahead and draw that in. And this half, because it's so big and you already have a bridge pointing up, has no choice but to go down. So this kind of violates the little rule that I gave you before, but as long as you remember it, you should be fine. So you could either put them both on dashes, or you could just draw it facing down. I think the easier way to draw it in this case is to draw it using a chair conformation, so I'll go ahead and do that, because that makes it more obvious what's pointing down and what isn't. And here you have the bridge formed. So that's going to be the answer to this one. Sorry, my chair isn't the neatest, but trust me, look at the picture. You could also, if you wanted to like make it more prominent that this bridge is coming up, you should draw it on wedges, but it's not mandatory. Okay, so this one is another special case of the Diels-Alder reaction, because in this case, since you're reacting it with the excess of the diene, you're actually going to get two reactions to get to your product. So starting with the first step, you're going to react it once, and you can go ahead and number them. 1, 2, 3, 4, 5, 6, giving you 1, 2, 3, 4, 5, 6. Because there is a triple bond on your dienophile, you're actually going to still have one bond left behind. So that means these CNs are not going to have any stereochemistry yet because they are sp2 hybridized. Your methyls on 1 and 4 are pointing away from the center, so they're both going to be on dashes. And now you can use this as your dienophile, your dienophile, again for the second step, because you have your double bond with an X group, I guess. So this is the second step. You're going to, again, react it with your diene. And this is going to give you, well, again, number it. Numbering is important. 1, 2, 3, 4, 5, 6. So now you're going to get a double ring. Ooh, I'm running out of space. I'll draw it down here. So now you're going to get a double ring where your methyls are still going to be in the same spot from before. You're still going to have a double bond on this end. You're going to have another double bond between your 1, 2, 3, or your 2 and 3. And between 5 and 6, now your CNs are going to be on dashes because they're pointing towards the center. And now they do get stereochem because now they're sp3 hybridized. And then 1 and 4, you're going to have 2, again, dashed methyls. So that's what your product is going to be. And I'll go ahead and fill it in. These are ones that he tends to use a lot, so I would just memorize the ones that I included on this exam. These are also straight from his lecture notes, too, in case you want to see his explanation. But drawn out neatly, this is what your product is going to look like. So F is an example of an intramolecular Diels-Alder, so you're definitely going to want to do your numbering with this one. 1, 2, 3, 4, 5, 6. And then you're going to draw your ring with the double bond between 2 and 3. And off of 5, you're going to have your CN. In this case, it's going to be on a dash because it ends up pointing towards if you redraw it next to each other. So CN is on the dash. And now you have 7, 8, 9, 10 coming off. So off of 4, you have 7, 8, 9. I'm running out of space. 10. So I'm going to redraw that a little bit more neatly over here. Oops. And this is the answer to F. Hopefully you guys remembered to pinch off the rest. Okay, so this one is going to ask you to do the Diels-Alder molecular orbitals. So if you remember, it's going to be the HOMO of the diene, and the HOMO is going to be one less node than double bonds that you have. So you're going to put one node in symmetrically, and the LUMO of the dienophile, and that's going to be the same number of nodes as the same number of double bonds. So you have one double bond in your dienophile, so you have one node. So you could set those up next to each other, and then all you have to do is fill in your molecular orbitals like I taught you before. And just make sure that whatever you put on the top here on your dienophile, you put on the bottom of your diene. and then make sure you flip it between the node. And that's the answer. Or you could have done the reverse. Okay, so for 1y, it says to write the mechanism of propagation steps in the following reactions. Be sure to show all electrons involved in bond formation and show movement of electrons with appropriate curved arrows. Using the bond dissociation energies, calculate the enthalpies, which is the same as bonds broken minus bonds formed, of each of the propagation steps and the total enthalpy of each of the reactions shown. Show the calculations. So for the mechanisms, he only wants you to do the 2 propagation steps. So we'll go ahead and do that for the first one. So the first step is going to be the breaking of the CH bond and the forming of the HBr bond. So one of the radicals is going to go back to this carbon, and one of the radicals, that's fine. And one of the electrons is going to form the new bond with the Br. So then you end up with the second step of propagation is going to be the radical on your alkane reacting with Br2. So the radical is going to make a bond with one of the electrons here, and then one of the other electrons is going to jump to the other Br. So in this case, you're forming a CBr bond and breaking a Br2 bond. And the product is going to look like this. Okay, and now when I'm going to do the enthalpies, so like I said before, it's going to be bonds broken. Actually, I'm not going to write it out. You guys should know by now that enthalpy is bonds broken minus bonds formed. So since we are breaking a CH bond, they tell you up here that the CH bond is 422 kilojoules per mole. So you're going to go ahead and do 422 minus what bonds are formed, and we form an HBr bond. And over here, they tell you that that's 368. So minus 368. And then you end up with positive 54 kilojoules per mole for your first propagation step. And then for your second step, you are breaking a Br2 bond. So up here, you can see that that's 192 kilojoules per mole. And you are forming a CBr bond, which they show you is a 301 kilojoule per mole. And then you end up with negative 109 kilojoules per mole. Combining these two, the delta H of the whole reaction, or the whole propagation step, is negative 55 kJ per mole. Okay, moving on to the next one. The first propagation step for NBS is going to be the formation of the allylic radical. So you start with your allylic Br, and one of the electrons from the H is going to go back onto the ring, and one of them is going to form the new bond with the Br. So in this case, you are going to break a CH bond, and you're going to form an HBr bond, which is similar to before. The only difference is that this is a double bond allylic to the H, so that actually has its own separate enthalpy, so make sure you remember that. Okay, moving on to step 2. Now that you have your radical, you're going to combine it with the Br. So one of the radicals is going to go back to the Br, and one of them is going to go to forming a bond. So you're forming a allylic Br carbon bond, and then you are breaking a Br2 bond. Okay, so the enthalpies for the first step are going to be, as we can see here, we broke this bond, so it's going to be 372 minus 368 because you formed an HBr bond. and that's going to give you negative 55 kJ per mole. And then for the next step, you broke a Br2 bond, which is 192. And then you formed a allylic Br bond, which is 247. And that is going to give you... Oh, oopsie, I messed this up. This is positive 4 kilojoules per mole. Sorry, my work got sloppy. And this is negative 5 kilojoules per mole. So the overall for this reaction, your delta H is going to be negative 51. Oops. Negative 51 kJ per mole. For the last question, it is a series of box problems. For the first step, you have to know what NBS does, and NBS is going to add a Br allylic to a double bond. So your product is going to look like this. And then the next step is a reaction we should all be very familiar with. It's going to be a SN2 reaction. So that's going to replace your Br with a CN. In this case, because we didn't specify, we didn't have to specify stereochem in the first one, you don't have to specify stereochem here, but that is the answer to that.